Bridges, section 8.6, quadratic and rational inequalities. I know this is kind of a weird section. This section comes right after 6.7 and before we go into chapter 7. Yeah, it's weird, but I know what I'm doing. Okay, so the first thing that I want to point out is that whenever you're solving a quadratic or a rational inequality, you have to look for the critical points. And the critical points are where the function or the expression is either undefined or equal to 0. So let's start off with x squared minus 5x is less than 0. So whenever you do these, you're going to want to make sure that you have 0 on one side of the inequality. And then factoring is going to be key. So what we're going to do is we're going to factor. So if I look at this piece right here, see if I can get my magic pen going here. So if I look at this piece, and I try to factor it, that would be, I'd have a common x, so I'd have x and x minus 5 is less than 0. And if you recall, if I said this were equal to 0, then I'd have x equals 0 or x minus 5 equals 0. Therefore, x equals positive 5. So what I'm going to do is I'm going to make a number line. So I'm going to put 0 on there, and I'm going to put 5 on there. And then I'm going to look at this guy right here. Since that's less than and not less than or equal to, I'm going to put open circles on my number line. And what you have here is you've got the number line split into 3 regions. So you've got this left region right here. You've got this right region right here, or the middle region, geez. And you've got this other region to the right over here. And so what we're going to do is we're going to pick a point from each region. We're going to plug it into this stuff over here, okay? And we're going to see what kind of number we get as a result. Now, I can either plug into this, or I can plug into the factored form. It doesn't really matter. So what I'm going to do is I'm going to pick a point from over here. So let's say -1. So what I do is I plug it in. So I can say -1 squared, which would be 1, minus 5 times -1, which makes 6. And that's a positive number. So I'm going to put a positive right here. Or what I can do is I can plug it into the factored form. So if I plug in -1, x itself would be -1, so that's negative. -1 minus 5 is -6, that's negative. And negative times negative is still positive. So either way you want to do that. So let's pick a point from in here. 1 would work, 2 would work, 4.95 would technically work, but 1 would probably be the easiest thing to plug in. So 1 itself is positive, 1 minus 5 is negative. Positive times negative gives me an overall result of negative. Or if I plug it into the original, it would come out negative. Now let's pick a point from over here. We could pick 10 billion, because that's bigger than 5. So 10 billion is positive. 10 billion minus 5 is also positive. So positive times positive is positive. Now, when I look at this, I've got to figure out whether I want positives or negatives. So when I look at this, I'm going to be looking at that piece right there. less than 0. Well, what kind of numbers are less than 0? Negative numbers. Therefore, I want the part that's negative. And now that I've got this number line drawn, all I have to do is write the interval. So that would be the interval from 0 to 5. Now, here's the connection with what we were doing before. If I were to graph y equals x squared minus 5x, I'd get a graph that looks like this. So that's 5. I'd get a parabola that looks like this, roughly. So when I want that to be less than 0, that means I'm talking about the part that's below the x-axis, the part that's negative. And that happens from 0 to 5. So there's the connection. All right, let's do another one. So what if I have 2x squared plus 5x is greater than or equal to 12? Well, remember that I've got to get 0 on one side. So I'm going to go ahead and subtract 12 from both sides here. 2x squared plus 5x minus 12 is greater than or equal to 0. Do my little factoring box here. Hopefully you haven't forgotten how to do this. 2x squared goes there. 5x, negative 12. This is negative 24x squared. Positive 8 and negative 3 add to give you 5, multiply to give you negative 24. Greatest common factor between that guy and that guy is 2x. 2x times x is 2x squared. That's a 4. That's a negative 3. So you got 2x minus 3 and x plus 4. 2x minus 3, x plus 4, greater than or equal to 0. Now remember, to get the points that go on the number line, 2x minus 3 equals 0, x plus 4 equals 0. Add 3, 2x equals 3, divide by 2, x equals 3 halves. And then this one, subtract 4, x equals negative 4. So, on the number line, I need negative 4 and 3 halves. Now, I look at this inequality right here. Whoa. And I see that that's greater than or equal to 0. So since it's got the equal to part, I know that these are going to be closed dots. All right, now I've got my regions to test. I don't know about you, but I like plugging into the factored version better than the unfactored version because I think it's easier to compute. So let's pick a point from here. Negative 5 would certainly work. So 2 times negative 5 minus 3 is negative. You could compute the actual number if you needed to, but that's negative. And negative 5 plus 4 is also negative. Negative times negative is positive. Now let's pick a point from the middle. Well, there's a really nice point between negative 4 and positive 3 halves, 0. 2 times 0 minus 3, so I'm plugging in right here, would be negative, and 0 plus 4 would be positive. Negative times positive is negative. And then we can choose a point from over here. 10 would work. 2 times 10 minus 3 is positive. 10 plus 4 is positive. Therefore, positive times positive is positive. Then the question becomes, do I want the positive or do I want the negative? Well, I look at this guy right here and I say, okay, what kinds of numbers are greater than or equal to 0? Numbers that are bigger than 0 would be positive numbers. Therefore, I want the positive pieces, that piece and that piece. So, I would have negative infinity to negative 4, union 3/2 to positive infinity. Now, occasionally something weird might happen. Let's say I have x squared plus 2x plus 1 is greater than or equal to 0. So, again, I got 0 on a side, so I can factor. Notice when I factor this, those are the same. So I would put negative 1 on my number line. Since it's greater than or equal to, since it's got the equal to part, that's going to be a closed dot. And now I have 2 regions to test. So if I test the region on the left, I pick a point that's smaller than negative 1, say negative 2. I'm going to plug into this one. You can plug negative 2 into that one and test the same thing. So, negative 2 plus 1 is negative. Negative 2 plus 1 is negative. Negative times negative is positive. Now let's pick a point from the other side. Say 0. 0 plus 1 is positive. 0 plus 1 is still positive. Therefore, positive times positive is positive. And once again, I look at this inequality right here. What kinds of numbers are greater than or equal to 0? Positive numbers. Therefore, I would want this, and I would want this. Well, if you look, that's everything. So the answer, or the solution set to this inequality would be negative infinity to infinity. Now, if I had changed this to be x squared plus 2x plus 1 is greater than 0, what would be the difference? Well, since the equal to part's not there, this piece would all of a sudden be open. And if that were the case, it would no longer be negative infinity to infinity. This would be negative infinity to negative 1, union negative 1 to infinity. Well, what if I had done x squared plus 2x plus 1 is less than or equal to 0? Yes, I'll go ahead and redraw the number line. So here's negative 1. This is closed. This is still positive, and this is still positive. So if that's less than or equal to 0, I only want where it's negative or 0. It's never negative. So it's only 0 at negative 1. So the answer would be negative 1, or x equals negative 1, if you will. And if I had done this as x squared plus 2x plus 1 is less than 0, then this dot would now be open. And if it's open, I don't have any solution at all. All right, we have a couple more things to deal with. We'll have to do them in the next video. See you then.